All right.
I missed that.
Breck stole my story about running over a puppy, so I'll skip it. Happy to have today Sean Taylor of Facebook. He's going to be talking about...
And Ben.
And Ben. Oh, dual presentation.
Yes.
Well, we're happy you're both here. And happy Facebook has put out this tool called Profit for doing time series forecasting built on top of PyStan and RStan. Take it away.
Thanks, Ben. Really excited to be here. Thank you so much for the invitation to come. And this has just been an amazing conference. I want to thank the organizers. I also want to take this opportunity to thank my colleague Ben, he'll be presenting also, but I've never been able to publicly thank him for doing all the good stuff in Profit. So anything that's good in this presentation, give him credit for, and anything that you don't like is probably my fault. So I'm really excited to talk about basically how and why we built Profit at Facebook and why we use it. I think a little bit like an economist, there's a supply and demand of things in a lot of cases, and I think for forecasting at a company, there's supply and demand. So we have lots of problems that are forecasting problems. It's not a very glamorous kind of problem because everybody likes to work on machine learning kinds of things. But time series forecasting is the bread and butter of business applications. And we have to make a lot of forecasts. There's lots of different people doing forecasts. There's lots of different kinds of forecasts. So this is the kind of at scale that I really want to talk about. It's not the lots of data kind of at scale. It's the a lot of people working with data on a lot of problems at scale. So many of the people at Facebook don't have forecasting training or expertise. And if you go and try to read up on forecasting, you're going to find that there's a lot of domain knowledge involved. People who are good at forecasting have been doing it for a very long time. So when you have a company with 20,000 people and thousands of them working with data, it can be really challenging for them to effectively produce forecasts because it's one of these things that you only have a very small number of people who can really do very well. And there weren't very many existing solutions or tools that we could really rely on. So there's Rob Hyman's very excellent forecast package in R, but it's pretty low level and it wasn't sort of something that would work out of the box for a lot of people. So I'm going to talk about supply and demand. Demand for business forecasts at Facebook is immense. There are many applications for forecasting Facebook data. We have sort of capacity planning problems, so just how many servers should we buy. All these things depend on sort of having some estimate about how many things we'll be doing in the future, how many users we'll be having, how fast will our data grow, how many photos are people uploading so that we know how much storage to allocate. Then kind of another interesting application of forecasts is goal setting and trying to understand how we're doing relative to some baseline. So almost every team at Facebook has sets a goal for their half, and they do it relative to some baseline. You can't just say I want this to grow by 5% if it's already growing at 10%. So you need something to to set your goal relative to. So forecasts are really useful for that kind of application. Then we have anomaly detection applications. So is something that's happening right now kind of weird relative to what we've seen in the past? And that also requires having a forecast of some sort. And then one of the interesting things is that once you make forecasting kind of easier for people to do, which is one of the goals of Profit, people come up with all kinds of other applications for using forecasts that we really didn't anticipate. So an example would be we have bug reports at Facebook. Everyone, if you're using Facebook and you're having a bad experience, you can file a bug. We actually forecast how many bugs people file, and then we can actually use that to staff people on call to respond to bugs, know when the bugs are going to really spike. So that's kind of an interesting application we hadn't thought about. So we have all these forecasts that we need. Who is going to produce them for us, and how are they going to produce them? So what's the supply? The supply is going to come from people actually doing forecasting. So this is the data science curriculum for the Masters in Data Science at UC Berkeley, which is a wonderful program. We hire a lot of people out of that program. And you can see they'll cover things how to use Python, how to do data engineering, applied machine learning, and then there's sort of the statistics for data science unit. And then within that, there's one course which as one component of the course will teach time series. So a lot of the people that we might hire may have only been exposed to a few days of instruction on time series methods. So you're really like living in a world where you have like all these very talented people. They know how to code, they know statistics, but they don't really have like the domain expertise in forecasting to be effective forecasters. And that's a problem we were trying to solve. Just another example of this, like one of my favorite data science textbooks is Advanced Data Analysis from an Elementary Point of View. This is Cosmas Shalizi. Sorry, it's not very Bayesian, but I think we can all agree Cosmas Shalizi is awesome. And this book is great, and then you sort of like have this dependent data chapter, and then there's just like one little section on time series in that. So like even if you read this whole book, you'd have to get to the very end, and then you'd get like maybe 40 pages on time series, and then that would be it. So it doesn't really like leave you as a data scientist the way that we're training people well equipped to solve forecasting problems. And just like some more examples of this, this is Stack Overflow Insights. So this is questions tagged with various tags. So you'll see machine learning sort of like growing at a very fast, almost exponential rate over the last few years. Everyone has machine learning problems, but then like time series sort of like putters along, and it's always been there as an interesting, important thing, but it's not the glamorous thing that everyone wants to work on right now. So making it easier for people to do it kind of like lets them go back to maybe the machine learning that they want to do anyway. So our solution to this problem of like having way more forecasting problems than we have people to solve them is to automate it in some way. And I'm not going to claim that we can completely automate forecasting as a problem. I think that maybe in the future we'll have some neural networks that can do it way better than humans. But I think for now we're kind of in the world where like it still needs some domain expertise. But we can semi-automate it. We can make it easier for people to do. And here's the way that we did that. First, we went out throughout Facebook and gathered a lot of forecasting problems. So what kinds of time series data were people producing within the company? And we found a lot of great kind of like interesting problems. And then one of the tricks is sort of like to find out what is common about all those problems. Like, is there a family of models that could model all the sorts of time series data that we have been coming across? And it turned out that they had a lot of patterns in common, and Ben's going to talk about that in just a few minutes. It's like, what are the common things that show up? And they show up again and again, and that means that you can build sort of like one model that will hopefully apply to a lot of the, maybe like, the Pareto distribution, like 80% of the problems can be solved by just like one simple solution, and then we leave the 20% for maybe more advanced forecasters. We build a tool that can solve most of those problems. So we gather up use cases. We come up with a solution that we hope solves a lot of them. And then it's sort of like a training and education problem. So can we get like adoption of the tool? Can we make the tool really easy to use, have a really simple interface, make it so that like people will who would never normally do forecasts will be able to do them now because it's like because we've taught them so much about how to do it. And this was a phase of the project that was not the most glamorous thing. Like we had already like built a model that we knew worked well on a lot of application data, but then we had to make it usable to a lot of people so that they didn't keep asking us for help using the tool. And that was like documentation. I think everybody in the room who's worked on Stan could say like we're all in agreement that like producing high quality documentation is one of the most important things we can do for a project, and that's sort of what came up here. And then finally, there's this like offering advanced features when necessary. So we don't want people to sort of like run a forecast and get a result and be stuck. And that was where actually I think building it on top of Stan was a really fruitful thing, because we have these priors and different parameters that the users can change, and I think of them as like knobs and levers that allow them to like not be stuck with the forecast that they get out of the box, but like inject their own domain knowledge about the time series in order to kind of like provide a more effective forecast. So now Ben's going to come up and talk to you a little bit about the nuts and bolts of how Prophet actually works, and then I'll be back a little bit later.
All right, so I wanted to start by showing you an example of the type of time series that we wanted to use Prophet to forecast. This is the number of Facebook events. So events is a platform on Facebook where you can create events and share events and invite your friends to events. And each dot here is the number of events created on one day, all right? And we have 3.5 years of data here. Each dot, 1 day, 3.5 years. So suppose that you are the events team and you want to set some goals for maybe 6 months from now. Say like how many events should we expect to have in 6 months if things continue as they're going? then what in practice would happen is the team would go to their data scientists to handle sort of all of their data science needs and say, hey, here's our historical time series. Can you produce a forecast for us and let us know where we should expect to be 6 months from now? Now, like Sean said, this data scientist probably doesn't really have a very strong depth of knowledge in time series forecasting, but they will quickly discover that there's an R package called Forecast, which is genuinely really great. It provides really high-quality implementations of some general-purpose forecasting tools. But if you take this time series and pass it into the auto-ARIMA function, which is this kind of all-purpose ARIMA model that does a lot of model selection for you. This is a forecast you get, which is not very useful, right? Now, of course, the reason why it performs poorly is because we're using it wrong. And surely all we have to do to fix this is to adjust some of the parameters to get a more meaningful forecast. So if you look at the doc string for this function, if you do a question mark auto.arima, this is a doc string. We can see what the arguments are. First, there's a time series, and then the rest are the optional parameters that we can use to tweak this forecast to get something reasonable. We have the order of first differencing, the order of seasonal differencing, the maximum value of little p, the maximum value of little q, the maximum value of big P, the maximum value of big Q, and many, many, many more, right? And so if you're an average data scientist, and you have a general idea that ARIMA is a model, but you don't really know how it works, your chances of being able to fit this forecast are zero. You really have no idea how to use these parameters to fit that awful forecast that we got. And this is true for any of these fully automated general purpose time series forecasting methods. This is the exponential smoothing function, which also does a bunch of model selection and provides an even worse forecast than the other one. So this is where we started with Prophet. We said, well, if you just take these fully automated tools, they don't work for the time series that we want them to work for. And this doesn't seem like that nasty of a time series. It seems like a relatively clean time series. So our goal was to develop a method that works for a time series like this, and that also has parameters that can more intuitively be adjusted by people without specific expertise in time series forecasting. So I'd like to now throw a question out to you. I keep saying time series like this. What are the features of this time series? Is it pure noise, or do you see some features in here that might be useful for predicting where we will be 6 months from now? Shout them out. All right, seasonality. So we'll start with right here. You can see this recurring dip right here, every summer and every winter. That's a yearly seasonality. What else? Yes, Christmas. So right before New Year, that week of Christmas and New Year, between Christmas and New Year's, there's this really strong holiday effect. Yeah, so if you squint your eyes a little bit, then you'll see this banding where there's like a dark band here, a light band here, another dark band. And when you look at enough of these time series, you'll recognize that as weekly seasonality. So like the day of the week effect. The scale is not, we're not able to share that, sorry. The scale is anonymized. All right, yeah.
You guys started advertising it better, maybe at some point at the very end.
Right, yeah, there's this trend shift right here. Everything was kind of puttering along, and all of a sudden, at the start of 2016, there's this really abrupt shift. Yeah, and a couple outliers. All right, well, we'll stop there because that's everything that I see. I hope that's everything that you see. If not, we should talk more afterwards. This is the same time series, this time colored by day of the week. And so you can really clearly see, these colors here are like Monday and Tuesday, down here Saturday and Sunday, this really strong and really clear day of the week effect. And yeah, those are the features, these multiple seasonalities, the strong holiday effect, and this trend change, and of course some outliers which are present in just about any data set. And these features are really common for a lot of business time series. And why is that? Well, this time series was generated by people doing things, people logging into Facebook and creating an event. And the things that people do are really, heavily influenced by things like the time of the year it is, or is it a holiday, what day of the week it is. And so any time series that's generated by people doing things is likely to have these types of features. And then trend change, I don't know what exactly caused that particular trend change, but we tend to see these types of things with new product launches or new features, right? Things where the business is changing in some fundamental way. So Profit is a model that is designed around exactly these features. It's meant to work well for time series that look like this, that have these multiple seasonalities, strong holiday effects, and these piecewise trends, because that's a really common use case that's not well supported by current methods. And the model is explicitly modeled around designed around these features. We basically, it's this decomposable model that says that the Y, the thing we want to forecast, is a piecewise trend, plus a seasonal component, plus a component for holiday effects, and then plus a noise term. And one peculiar thing, or one difference between Profit and most time series models is that Profit does not explicitly evolve in time like an ARIMA model would. It's actually a regression model. Right? So we treat time series forecasting as a regression problem. And what this means is that our noise model is incorrect, but we buy a lot by doing this. The first thing in terms of usability. So first, this piecewise trend. How do we have a model that is able to identify, automatically identify where the trend changes? Well, in a regression model, this is easy to do with L1 regularization. Or how do we model multiple seasonalities, right? This is easy to do with this Fourier series trick, which you can read the paper about if you want to see how that works. How about holiday effects? These floating holidays like Thanksgiving or like Lunar New Year's that appear on different days of the year each year are really obnoxious in an ARIMA model. But in a regression model, it's just a dummy variable. It couldn't be easier. So we gain a lot in terms of how straightforward it is to set up this type of model, and then also in terms of how people are, the familiarity with the users. We talked about how lots of data scientists don't have a lot of background in time series analysis, but there's one thing that every data scientist knows, it's regression. So by setting this up as a regression model, immediately all of the users have intuition to it, they know how to extend it, they know when it might not work, and it provides us a lot of usability. And I'll talk a little bit more about that noise thing in a minute. So this is also very easy to write down in Stan. This is the Stan model for Profit, for one of our, we have a couple of different models with the trend. This is for one of them. And basically it's just, we have a bid chunk here that describes this piecewise linear trend, and then we have a bid linear component, this x times beta, which incorporates the seasonality and these dummy variables for the holidays. Yeah. Yeah, so I'll try to get into that in just a second. I think actually maybe, oh, yeah, so then the question is, does it work? Well, we wouldn't be here talking to you if it didn't work. This is the Profit forecast for this time series, and you can see it does a really great job at detecting this, the yearly seasonality and projecting it forward, and the weekly seasonality also. And automatically picks up this trend change here. And I should say that this is with all default settings. All we do is give it the time series, and it is able to fit everything nicely, which we're not too surprised by because this is really the model's designed around time series that look like this. One of the advantages of this decomposable model is that we can look not only at the estimates, but we can also look at each of the components. So we can look at the trend, right, where we can see this slow decline and then the sharp increase upwards. We can see the weekly seasonality component, right? So this is where the model has now estimates for the Monday and Tuesday effect, and we can see it decay throughout the week. And then the yearly seasonality. We can really clearly see this drop in the summer and then the really big drop at the end of the year. And this provides, so not only can we get then an estimate, we can also get insight. And that's really valuable for teams and for data scientists to be able to understand not only what's happening, but kind of why is it happening, what are the relevant cycles, and how can we then better understand those to understand the system we're trying to forecast. All right, so I'm going to now dive just a little bit into some details of the one component of the model, which is estimating uncertainty. And this really gets at the heart of the difference between an autoregressive model that explicitly evolves in time and a regression model. So there are three main components of uncertainty in Profit, and I think in forecasts generally. One is uncertainty in the parameters, right? So if we're estimating these trends, what's the uncertainty in our estimate for what that actual slope is? And we can estimate that parameter uncertainty for free thanks to, we just do MCMC and Stan. So that's really fantastic. The second component of uncertainty is just the variance in the outcomes, right? There's always going to be some variability. This is just that noise term, which we are also able to model and estimate easily. The third part is uncertainty in the future of the trend. Right? We saw that in this time series, we had this really big trend shift. And if we're going to project forward our uncertainty for the future, it should somehow incorporate the fact that the trend might change again in the future. Right? If we've seen trend changes in the past, we should certainly expect them in the future, or we might expect them in the future. And this is something that if you have an autoregressive model, you'll sort of learn this. And these time series models, that's where you did this extrapolating uncertainty. As you move further into the future, you have higher uncertainty, right? This sort of growing uncertainty with time. And a regression model won't really give you that. And so what we do, so we kind of tack something on in addition to be able to handle this in Prophet. And let me now explain to you how that works. So the trend model, like I mentioned, is this piecewise trend. And in this figure at the top, you can see all these dashed lines. Basically, it's a piecewise linear function, and those dashed lines are all of the segments, right? These are the potential change points where this piecewise function is able to change. Now, the actual magnitude of the slope change at those points, at each of these segments, we infer. It's a parameter. Each of those magnitudes is a parameter in the model. And this figure here shows you the fitted or the inferred slope change at each of those points. So you can see, and we put a sparse prior on it, so it allows us to have kind of like a sparse number of these change points. So you can see what happens in practice is most of them are very close to 0, and then it picks up that there's really just this one substantial change point at the end, which is consistent with just looking at the data. So then how do we take this and use it to try and estimate what the uncertainty in the future will be? Well, the first thing is we estimate this trend change distribution when we're fitting. We do that anyway. And then at predict time, once we have a chunk of dates for which we want to make predictions, we'll then sample future trends from this distribution, right? So we'll say that at each point in the future, there's some chance of there being a large trend shift, and we'll sample it from this distribution and simulate what the future trend shifts might be. And so essentially we're saying that this gives us a distribution of where the trend will be if the future sees the same frequency and size of trend changes as the past. Is that a correct assumption? Certainly not. Is it a useful and reasonable assumption? I would say so. And this is what it gives us in practice. This is for this events time series, where, as you recall, there was really just this one big trend change in the past. And so in the future, you can see some fanning uncertainty as we project forward, which comes because the longer we go, the higher the probability of having a large trend change. And so we're able to integrate over the distribution of trend changes that we observed in the past to give us uncertainty in the future. All right, so that's a little bit of insight into one aspect of the model, and especially it's important for how we treat this time series forecasting problem as a regression problem. There's a lot more you could say about this, which we say in the paper. So read that, and I'll turn it back over to Sean.
Thanks, Ben. Sorry to disappoint all the Bayesians that it's not like a fully generative model, but it works really well, so that's great. So one of the upshots of like implementing this in Stan with real priors and having like, it's not exactly a generative model, but it has like human interpretable parameters, we think, that people can get intuition for, I think, pretty easily. So the first one is we can change the priors on like whether there is seasonality or not. So we can say like, oh, there should be a lot of seasonality in this time series. Let it sort of like overfit or fit the historical trend or the historical seasonality very well. Day of week, you can have priors on day of week effects. So you can say like, I don't expect there to be a lot of weekly seasonality in this time series. How often we expect change points, we have a prior on that. And if you turn that knob like to like, that it's if you have a very like high variance in that prior, then it's gonna like fit a lot of change points, and then it's gonna fit a very flexible function in the historical data, and then it's going to extrapolate like something that has like a very local trend change. And that's going to lead to a lot of uncertainty about the future because your change points are going to be large in magnitude. So if you sort of like, you get this nice trade-off where like, if you fit a very like unbiased model in the historical data, you get a very large fan out of your confidence intervals in the future. So that's a nice knob that we let people turn. We have different functional forms for growth. So Ben presented linear growth, which is just piecewise linear. We also have piecewise logistic curves, and people have talked about implementing other sorts of like piecewise continuous other functional forms, not too complicated to add. We also let users add covariates to the time series. So if you have covariates in the past that you also have in the future, you can add those. Those are just regression coefficients. That's one of the benefits of having it be a regression model. Holidays work the same way. You can just pass in a list of holidays. And we also let people add custom seasonality. So even though weekly, daily, and yearly are sort of like turned on with some heuristics, like if there is enough data, then we will use yearly seasonality. If you have more than a few days of the week, we will use weekly seasonality. You can also add custom seasonality. So if you know you have a weird one in your time series. And then finally, a parameter that we let people choose is like whether you just want a map estimate or you want to sample from the posterior. So by default, we only provide uncertainty about trend changes in the future, but the parameter uncertainty is not baked into the model. We just provide map estimates. And that allows Prophet to be really fast, so you can iterate on models really quickly. Like it should fit in under a second. So that allows you to say like, oh, I'm going to try a lot of stuff very quickly. And that's a real win for users who are trying to gain some intuition about how the model actually works. But then at the end, you say, oh, I'd also like to factor in uncertainty about my estimates of my parameters. You can turn sampling on, get posteriors, and then we'll provide uncertainty about all the parameters. So it's a nice little like trick for the users to get fast feedback when they need it, and then finally productionize a forecast. So you kind of like get some intuition for how we actually use Stan. There's just like this underlying kernel of a model that is implemented in Stan, and then we provide like, we take data as an input, we adapt it into a way that makes it easy for Stan to consume, and then we adapt the output from Stan to make it easy for the user to consume like what the output of the model is and inspect it. How does it work like kind of under the hood? This is very similar to I think how like, you know, RStanArm and like, other packages that sort of like use Stan tend to do is like you compile the models at install time. So when you download Prophet, there's a step where we take the Stan models, compile them, and cache them. Then at load time, at the time when you want to use the package, we will like unserialize those models and then make them available to the program. And then it's pretty straightforward to just like call Stan. And so there's no real like magic there. It's just kind of like what everybody else is doing. We do have some pain points with Stan, and I'm just kind of like seeding the community for maybe these are the kinds of things that we could use help with. Are basically just like this compiling model step is sort of fragile. So most people who use Prophet have problems at install time, but once they've got it installed, like things just work fine. I think that this is kind of like a common pain point. There's some upstream Stan behavior that we can't really turn off, so everyone's like, why is there so much log data on my screen? But and then there's sort of like rapid iteration can become hard when you have to wait for models to compile. So like, you know, that's something that I'm not sure we're going to be able to escape, but it's definitely something that like when we're trying to try new things, it can be a little bit harder than we'd like. The upshot of using Stan to implement the procedure was that implementations for R and Python were like pretty easy to build. So we first built a Prophet in R, and it took like basically just like a couple days to code up once we had the idea for the procedure. Then once we were like, hey, this works really well in R, porting it to Python also took like maybe like a week. And now we have these two parallel implementations that both work. They're both feature equivalent. And this might seem like kind of a minor thing, like, oh, like we'll just, if people want to forecast, they could just use R. But actually, like implementing in both languages, I think caused like a lot of extra people to be able to use forecasts that wouldn't normally be able to do so. So at Facebook, we're about 50-50 for analysts using R and Python. And then we found out like in the real world, it actually tilts like, at least downloads wise, more heavily toward Python. So if we had only covered one of these two languages, we'd be leaving like 50% of the data science market like unfulfilled, or those people would have to go and use a language that they maybe aren't used to using. And I can speak for at Facebook, it's much easier for us to productionize Python code than it is R code. So like there's a lot of use cases where if we didn't have it in Python, then it just wouldn't be used. Profit is just sort of like one example, I think, of a future where we start democratizing statistical tools. So everybody in this room is like really smart and knows how to build models in Stan, but that's not like the normal person at a company who needs to get things done. And those people, whether you like it or not, are going to like do statistics-y things. So it's better if we provide them like, some framework for doing that instead of just sort of like, giving them a bunch of packages and like let them loose with like without a lot of guidance. So Profit's a very opinionated tool, but it helps people solve real problems, and it covers like a lot of use cases that a lot of people commonly come up with. So here's the way that I think about it: is that users sort of like have some raw data, and one of the things that they're good at is making the data into another format. So we expect the input to Profit to like be a data frame that looks a certain way, and it's easy to articulate that requirement to users. And then after that, like we can provide basically an abstraction layer on top of the data for the user. So the Profit object, once it's fit, is basically like a view on the data that can provide different functionality, like some visualizations, it can provide predictions, it can provide diagnostics. This playbook is super generalizable to other kinds of problems, and it's going to help users use like we're going to scale statistics to like way more people that way. So another way to think about like the way that we thought about Profit was this is like the sequence of steps that you go through before you actually like have impact from the work that you do. You start with like, I have an idea for how to solve a problem. Then you have something that like might work for you. Then you have something like the working prototype phase is the most exciting one. It's like it worked for me like one time out of like the 10 times that I tried it. Like, the code that's like fragile, but you know that it works because it's worked that one time. Then we have like the quality code phase. Like we had a phase where Profit was like usable for engineers at Facebook. So like if we coached them and we sat down with them and got them to use it, like they could use it. But then packaging it up into like a tool or service where like people who are not experts in statistics can use it was like a huge breakthrough in usability. And it was like a big trend change in how many people were using it for forecasts at Facebook. So I think that this path is sort of like a very common path, but a lot of people stop at like working prototype and they don't go the extra like couple steps to like make something that really democratizes the tool. We have tons of other potential applications for things that could be built on top of Stan or other statistical procedures at Facebook. Analysis of experiments happen a lot. We also run tons of surveys at Facebook, so we'd like to be able to analyze those and using state-of-the-art kind of methodologies. Observational causal inference in the cases where like we're unable to use some sort of randomization. Anomaly detection comes up all the time at Facebook, and then there's like all kinds of clustering problems. These are the kinds of cases where like you can expect the user to like make the data in the format that you want, and then apply a procedure to it, and then apply like let that procedure provide some functionality on top of the data for the user. So we anticipate being able to build more and more statistical tools that help solve more and more problems for people at Facebook, for people that are not experts in statistics. And then maybe like we did with Profit, provide these advanced features for people who really want to get under the hood and like make improvements so that if they really do understand how the procedure works. So my takeaways here are, number one, I think it's interesting that the forecasting problem at Facebook, I think, was not so much of a technical problem as a people problem. It was like, the actual forecasting procedure as been presented is not really mind-blowing probably to a lot of people in the audience. Something that like, if you were faced with a time series like that, I think a lot of you could have coded up something like that. But it's really about like putting that power in the hands of a lot of people so that we can scale that to many people and many problems. And it's not scalable just to have like one person who's smart, who knows how to do something at a company. You need like a lot of people who are empowered to do a lot of things. Profit's a simple model, but it works really well. And I think it's an example of sort of like putting your known biases into a model and letting those biases sort of like help the model extrapolate well. Like we know a lot about what these time series look like because we have a large collection of them, and it tends to work well for people at other companies as well. So we've been pretty excited to see other people get good results because their time series actually look a lot like ours. Stan allowed us to build it very quickly, and it also gives us like a lot of these cross-platform benefits, and we look forward to sort of like benefiting from all the improvements that people are making to Stan downstream or upstream. And then there's sort of like, if you think about this as just a specific instance of the general problem of there's lots of statistical problems at companies and in academia that need to be made as user-friendly as possible, because those people are going to solve those problems whether you like it or not, and they're probably going to do it in a way that is worse than if you provided them a good tool for doing it. So just to wrap up, I encourage you to try out Profit, go download some time series and forecast them and tell us how it goes. In particular, we'd love to hear when it doesn't work well for you. So if you have cases that are sort of like corner cases, like tell us, and that's something that we'd love to be able to like add some way of detecting that or checking for it, or maybe some option that allows you to kind of move forward with your forecasting problem. Help contribute to the project. So there's lots of different issues that could be easily solved by a lot of the people in the room. So we'd love to get your help if you have time for it. And then finally, read our paper. So if you're interested in more details on like how the procedure works, we have a forthcoming paper in the American Statistician about it. So thanks so much for your time, and thanks for supporting Profit.
Okay, we have a few minutes for questions and tons of questions. Okay.
Oh, okay. Thank you very much. This is a really cool looking tool. You said that you modeled the errors as IID, and then you said you were going to talk later about that assumption, and you didn't. So I just wanted to ask.
I'm gonna hand that over to Ben because he's the one who promised you that.
So the errors are IID, or they're modeled as IID. But then the part that isn't considered IID is this extrapolation of the future trend uncertainty, right? So that's where we say, what's our uncertainty in the future trend? But the daily errors we just model as IID.
There's nothing stopping us from adding some sort of autoregressive component to the error structure in the model, except for that we don't in Profit enforce that your data are sort of like evenly spaced in time. So that allows us to like circumvent having to do any interpolation that you normally have to do in other time series methods that are recursive. But because we're just fitting a curve, you can have like missing data, you can delete your data, and it will just infer where it was. So we get a lot of benefits from not having to think about having a regularly spaced time series structure. But I think if you needed autoregressive components, we could easily build it. We just haven't really come up with like why we need that yet.
I'm very interested in the at-scale stuff to do with people. So I've got lots of questions, but the main one is that often a forecast for one thing will be an input to a forecast for something else. So a forecast for user retention could be an input to a model about daily active users or something. How do you solve that problem and manage all that stuff?
That's a good question. We sort of like punt on that in some ways and let our users decide like how they're going to use the forecast. And I know that can lead to some missed opportunities, but typically the way that Profit is used in practice in batch is like that people will construct workflows where, with a tool like, what's the Airbnb Airflow tool? Like we have something kind of similar at Facebook where you can like have an directed acyclic graph of like tasks, and some of those tasks are like forecasting tasks that like put forecast in tables, and then people just build on those downstream. So the short answer is we don't know how people are doing. There's a lot of people using it, but we kind of like have some intuitions about what people are doing.
Hi. So I picked up Profit and I put it into production at my company, and it's like working really great. My coworkers.
I did not pay Chris to do this.
Yeah, I know, it's working great. But we do have one particular problem, which is that, of course, every holiday it says, hey, there's a bunch of anomalies, and I know that you can feed in a holiday dictionary. But I noticed that there's a rebound effect on the days after the holiday, and I was wondering if the holiday feeding in holidays would also take care of that rebound type problem.
Yeah, so what we've seen the same thing in a lot of our time series, and what we do and what we typically recommend people to do is you can specify the holiday as a holiday, but then you can also specify the days after the holiday as a holiday, and so you can learn the rebound in the same way you learn the drop on the holiday. So.
I was wondering, in your problems, how well calibrated are the uncertainties on future predictions? Like, do they actually fall into the 95% confidence interval 95% of the time?
That's a great question. The answer is no. The answer is it depends, right? So if the model were perfectly specified, then the answer would be yes. But there's definitely misspecification in every problem. How much, it really depends. And so generally, I think they're good enough to be useful, but I would not expect them to have accurate coverage. And we're very careful in our documentation to not call them confidence intervals. So I think in terms of the REMA results that I showed you, the main issue with the REMA results that I would see wouldn't necessarily be the poor error estimates, but even the mean estimate was just forecasting constant. It didn't pick up any seasonality or anything. And in terms of our uncertainty estimates, this is sort of that procedure I very at a high level outline where we simulate from our generative model of trend changes and simulate that. We simulate that forward, and that's how we get some uncertainty estimates.
One more question.
So I would like to ask a little different question. It's about the data gathering process, that people use to get the data that's in this model, and kind of got the impression that that's something that is not a big problem for you, whereas in many, many companies, data discovery and data quality and all the, master data management, all this stuff is a huge problem. So are you just solving that really well at Facebook, or how do people get their data into so that they can now forecast?
Yeah, I don't have that's way beyond the scope of what we sought to solve with Profit. And it is, I think every organization faces this problem. I think Facebook is good at it, but not as good as other places that I've talked to. And we do sort of take great pains to document our data really thoroughly. A lot of good data comes from good logging. So we have really excellent logging tools that produce very standardized output formats with a lot of pre-baked documentation. And then a lot of it's sort of tools for data discovery. So you just build tools to solve. Facebook is a tool building culture. We build tools for everything. And so we have many, many tools for helping people find data, helping people tell people about their data and stuff like that, and then ensuring data quality. So just sort of a long tail distribution of tools is my short answer, but it's a culture problem too. But that's another whole. You could do 2 talks on that.
Okay, let's thank Sean and Ben one more time.